let's begin this parallel session. The topic is concept and graph-based reasoning. The speakers is Jiayuan, Tongzhou, and Hao. Hao Tang, it's not Hao Su. Okay. So thanks for the introduction of the speaker. So I will skip this. Let's talk about the topic. Human beings have the ability to adapt their learned concepts and skills to the new tasks. For example, there are two different instances of the video game Pacman. If a human has been trained in the left environment, he or she can also solve the right environment because the underlying game mechanisms are the same and the visual observations are similar. Task level generalization is achieved. Task level generalization is achieved when the policy learned for one task can perform relatively well on an unseen but similar. However, current learning algorithms, especially end-to-end learning methods, failed to achieve that generalization. Therefore, we ask such how to achieve task-level generalization. We may base on our policy on objects in this game, like the yellow Pacman, white dots, and ghosts. The policy based on this kind of abstraction can be easily transferred to the right environment. We only need to control the yellow Pacman to head to the white dots while avoiding the ghosts, which we can generalize to any maze, any configuration. Another example is writing about humans build an abstract world model in their mind based on what they are able to perceive. We make decisions and take actions based on this abstract world model. As you can see, the appropriate abstraction is critical to generalization. Then, what kind of abstraction is beneficial to generalization? We believe that a good abstract world model should be object-centric and only consider the task-relevant objects. Obviously, we do not need to model details like our hair, skin, and other irrelevant parts in order to write a line. In fact, we only need to model the left leg, right leg, and the pendles. We may also associate some task-relevant properties with them, like the positions. Based on the abstracted objects and their task-relevant attributes, we are able to infer what action we should do. For example, push the left pendle or the right. With this skill, we can ride almost all kinds of bicycles without learning again. Graph neural networks are suitable for our object-centric representation. The objects and their relations can form an object-centric graph. However, current graph neural networks have several drawbacks with regard to the generalizability, which will be introduced in Hao Tang's presentation. So today's topic will be how we can achieve a better generalizability. The first talk will be T, task-driven entity abstractions. It answers the question how to acquire object-centric representations. And the second talk will be iterative homogeneous GNNs. It answers the question how to design generalizable graph neural networks. Yeah, it's the end of the introductions. So let's welcome Tongzhou to continue to introduce the T. Thanks.
Okay. Hello, everyone. Thanks, Jiayuan Gu, for the introduction. My name is Tongzhou Mu, and today I will introduce our project, Task-Driven Entity Abstraction from Visual Observation, and the abbreviation is T. This is the outline of my presentation today. So first, let me give a brief introduction to this project. So as Jiayuan Gu introduced, we believe that an object-centric representation would be a good representation. So the focus of this work is object-centric representation for environment modeling. And based on this, we have two specific objectives. First, we want to learn appropriate objects or task-relevant abstraction from the visual observation. And second, we want to achieve task-level generalization. You may feel these two objectives are a little bit abstract. I will explain them in the two specific tasks we used in this project. Okay, so the first task we considered is the summation of digits. You can take a look at the pictures. We put several digits on a background image to create a new image. The digits are from minutes dataset, and the background image is from CFAR or ImageNet dataset. Then the task is to calculate the sum of the digits. Since our objective is to find task-relevant objects and achieve task-level generalization. So in this task, the objects we want to find are the digits in the image. Note that the other objects in the background are not related to our task, so we need to ignore them. And we define the task level generalization in this case as generalizing to the test set. The train set and the test set may have different backgrounds, different digits positions, and a different number of digits. To achieve this kind of generalization, the model has to learn the underlying rules. That is, have to learn to find the digits and add them together, not just memorize the label of each image. And the second task is the famous video game Pacman. We need to navigate the yellow Pacman to eat all the food, which are white dots in the images. To make the object discovery not too trivial, we also replace the backgrounds to CFAR images or ImageNet images, like this. In this task, the objects we want to find are the yellow Pacman and white food, and also the other objects in the background are not task-relevant objects. We need to ignore them. And we want the agent can generalize to the environment with a different number of food. For example, we train our agent in the environment with only 2 food, and we want it to generalize to the environment with 10 food. This is our task level generalization in this case. Okay, so far I have explained our 2 objectives with 2 specific task examples. So to achieve these 2 objectives, our basic idea is using tasks to guide the discovery of objects. So we call our method as task-driven entity abstraction. In our experiments, we showed that both objectives can be achieved by our task-driven method. So let's take a look. First, we found that introducing tasks can help improve the abstraction. The images are the object discovery results from 2 methods. The top row is from previous purely reconstruction-based method, space, and the bottom row is from our task-driven method. The green boxes is the ground truth, and the yellow boxes are prediction. You can see that the previous purely reconstruction-based method captures a lot of wrong objects in the background. They are not digits. However, our task-driven method accurately captures all the digits and only digits, because only those digits are related to our task, which is calculating the sum of the digits. So in this example, we found that tasks help us define the objects and the attributes of the objects. Second, we found that the object-centric abstraction helps task-level generalization. We train our Pacman agent in the environment with only 2 dots, and the red boxes are the task-relevant objects found by our model. As you can see, with appropriate abstraction, our model can zero-shot generalize to the environment with 10 dots. In this example, we found that objects provide appropriate input to policy or task solver. Okay, now let's talk about how we achieve the above-mentioned results. I will explain our method in detail. Since our model is a little bit complicated, I will first introduce the Inference-time Architecture, and the model training process will be introduced later. Our model consists 2 parts. The first part is the object proposal network, which takes an image as input and outputs object proposals. Here, our object proposals include 3 latent vectors, which represents the bounding box of the objects, the content in the bounding box, and whether this object is present when solving the tasks. And we use variational inference to approximate the posterior probability of the latent variables. So this is the first part of our model. Let me explain the object proposal network in detail. As I mentioned, this part is used to produce the object proposals, which includes 3 different latent vectors. Z-press represents the presence of the object. Z-where encodes the position of the bounding boxes, and Z-what encodes the content in the bounding box. All of them are random variables which are sampled from corresponding probability distribution, and the parameters of this distribution are produced by our object proposal network. So look at this figure. Inspired by modern object detection architecture, we use an anchor-based object detection method. That is, we divide the image into several local cells and put anchors into the cells. Then we use bounding box regression to localize the position of each object. Finally, we get the parameters of the bounding boxes. Similarly, we can also produce the parameters of other 2 distributions. Okay. Then the second part of our model is task GNN. The task GNN takes the object proposal as input and produce a task-specific output, for example, an action. The reason we choose GNN instead of MLP is that we need to handle variable number of objects got from the object proposal network. Since we are using a GNN, we need a graph. The graph nodes are objects from the object proposal network, and the graph edges can be determined according to the task. For example, if the task is related to the object relations, we can add edges between every node pair, so we get a complete graph. Otherwise, we may put no edges in the graph, or other kind of graphs can be used if it's beneficial to solving the task. Okay, so far I have introduced the inference-time architecture of our model. Then the question is how to train it. We train our model. So here you can see there is a task loss. The task loss can come from a reinforced learning algorithm. For example, we use TD arrow in our experiment. This is the loss function in DQN algorithm. And we train our model in a typical end-to-end learning fashion. That is, we need to propagate the gradients from the loss function all the way back to the network parameters. However, the latent variables are sampled from a distribution, so we have to come up with a strategy to estimate the gradient with respect to the distribution parameters. Here, z-where and z-what are continuous variables, so we can use reparameterization trick to estimate the gradients with respect to the distribution parameters. But z-press is discrete because it's binary, yes or no, so we cannot use the reparameterization trick for it. Instead, we use Monte Carlo sampling to estimate the gradient with respect to p-press. This is also called reinforced algorithm. This is a more general method compared to reparameterization trick, but it brings large variance due to the sampling process. So basically, this is our training process. Looks great, right? However, it fails to converge to a reasonable good solution in limited time. So why does it fail? There are several reasons, but the major one is that the joint learning of object proposal and task net is so hard. Learning task net without appropriate input is hard, and learning object proposal net without reasonably good task net is also hard. And if we combine them together, the search space of the joint learning problem is super large. And there are also other reasons. For example, the sparse reward problem. In Pacman game, the agent will only get reward when he eats food. So the reward is pretty sparse in the whole process. And also, we need to sample discrete random latent variable z-press. The sampling process introduces a large variance and makes training unstable. So basically, this is a chicken or the egg problem. The policy and abstraction are hard to learn without each other. So we want to ask such a question. Can we solve one of them first? The answer is yes. Now, I'm going to introduce a technique we proposed, which is called induction by distillation. First, a fact in reinforcement learning community is that many tasks can be solved or overfitted by reinforcement learning algorithms. For example, the deep QNet algorithm can overfit our Pacman game. Based on this fact, our first step is to pre-train a CNN-based DQN to overfit the task, say the Pacman video game. This is not very hard. And then our second step is to train the task GNN on the images with the Q values. Let's look at the figure. We use a pre-trained DQN to collect the images from the environment and label them with Q values. And we use our architecture to take the images as input and produce a predicted Q values. And then because we have the Q values as labels, we can calculate the MSE between the predicted Q values and labels. We call this loss as the distillation loss. In this way, we actually convert a reinforced learning problem to a supervised learning problem. The network can get much denser supervision signal on every input image and greatly reduce the optimization difficulty. Let's analyze the process again. Here, the CNN-based DQN is a teacher, which is easy to train, but it will overfit. And our object-centric model is a student, which is hard to train by itself. But it can distill knowledge from the teacher and even perform better than the teacher in terms of generalization. This is pretty interesting. The teacher just overfits to the environment, but the student can generalize well. This also proves that the object-centric abstraction is critical to task-level generalization. Finally, this is the whole pipeline of our model. And our total loss function consists of several terms. Let me explain them one by one. The first term is L distillation, which is I just explained above. This is the distillation loss based on the task. And the second loss is reconstruction loss. So we also add a reconstruction loss to make the training process easier. To be more specific, we reconstruct the image based on the object proposals and the background, and use this as an auxiliary loss to guide the learning of object proposal network. This is the auxiliary loss. And the third loss is a KL divergence loss. We provide prior distributions for the latent variables, and the KL loss term is used to control the distance between the learned distribution and the prior distribution of the latent variables. And the last loss is a reinforced loss term, which is used to train the p-press, the presence probability of the objects. It is computed based on the distillation loss and the reconstruction loss. Okay. So this is a detailed network architecture of our model. So if anyone is interested, I can introduce it later, but skip it for now. So let's move on to our experiment section. This is a visualization of the object discovery results from the baseline model and our method. The green boxes are ground truth, and the yellow boxes are prediction. The left two columns are from space, which is a purely reconstruction-based method. You can see that it captures a lot of wrong objects in the background, not digits. And the right two columns are our task-driven method. It accurately captures all the digits and only digits, because those digits are related to our task, calculating the sum of the digits. And this box plot compares the object detection result quantitatively. Our metric is the average precision at IOU 0.25. The rightmost column is our method. It provides much better object detection results than the leftmost baseline. And the middle one is our method without task supervision. It doesn't perform that well. This also proves that introducing tasks is beneficial to object discovery. And here we show our model can generalize well can achieve better task level generalization. Our metric is task accuracy. Here we mark a sample is correct when the prediction summation and the ground truth summation, the distance between them is less than 0.5. You can see that if we use a plain CNN to overfit the trained data, it can never generalize to the test data. But our task-driven model can generalize well to the test data. Okay, so this is the experimental results from the summation of digits experiment. Now let's look at the Pacman experiment. So you have seen these two videos before. Let's move on to the next slide. These figures show that how well our agent generalized to the environment with more dots. The x-axis represents the number of dots in the environment. The y-axis is the mean episode reward got by the agent. The blue curve is our task-driven method T. The orange curve is a CNN-based DQN model, and the green curve is a random policy. And we train our agent in the two dots environment and test it in the environments with more dots without any fine-tuning. You can see our model can outperform other baselines by a large margin and generalize to up to the environment with up to 10 dots. And we also did another experiment called Pacman with Distractors. In this experiment, we put several distraction objects in the image. Here, only the yellow Pacman and white dots are task relevant, and the red dot and the blue triangles are task irrelevant objects. The ground truth bounding box are annotated in green, and the prediction bounding box are annotated in red. You can see that the previous method without task supervision will also treat the blue triangles and the red dots as objects because visually they look like objects. And our task-driven method will accurately capture the Pacman and the food while ignoring the blue triangle and red dots because they have no contributions to the tasks. Okay, so that's all for the experiment section. Now, let me summarize our work. So there are two important messages we want to deliver. First, the basic idea behind our approach is induction by distillation. That is, objects emerge as we seek for interpretation for a policy to solve the tasks. And the second, we showed that object-centric abstraction helps task-level generalization. Okay, so that's all for my presentation. Thanks for listening.
And my topic is towards scale-agnostic graph problem solving by iterative homogeneous graph neural networks. And my name is Hao Tang. So the problem we want to solve in general is how to generalize knowledge learned from small-scale data to much more complex, larger-scale ones. And this is just how people learn and apply knowledge. For example, people can easily transfer or generalize policies learned from small mazes to larger or more complex ones. And the Newton's laws and other many physical laws, they are induced or summarized in the small experiments, such as this Newton balls. But you can generalize the policies and knowledges to the much more complex modern high buildings. So there are many more other examples like this with the scale-agnostic properties. Given the expressiveness of the graphs, all these problems can be reduced to the graph representation learning problems. So we want to train our models on smaller graphs while generalized on much larger graphs. Here shows an example of the shortest path. We actually achieved that we can train our models on graphs with no more than 30 nodes, but we can generalize to graphs of diameters as large as 1,000. And here shows the outline. We will firstly briefly introduce the background about graph neural networks and then improve the graph neural networks generalizabilities from two perspectives with respect to scales. First is about the graph diameters and the path lengths, and we introduce a differentiable iterative architecture so that we can have unlimited receptive sizes. And the other is about the representation scales, how to generalize with respect to them, and we introduce the homogeneous pair. Finally, we will show some experimental results. So there are many real-world data that does not have a regular structure such as the image or languages. They are just the dynamic graphs with dynamic sizes and dynamic structures. For example, for the social networks, knowledge graphs, and roadmap. And it's not trivial to design neural networks to operate on them. And currently, there are typically graph neural networks are recently developed in the recent years. And here we show that's the most popular framework, which is the message passing framework. And you can consider it as a generalized message passing by neural networks. And it has neural network modules for calculating messages and then aggregating the messages to the central node and updating the central node's features. All these modules are shared by all the nodes and edges. So given this message passing layer, you can have the neural networks to approximate the permutation invariant or equivalence functions, and they can support graphs of arbitrary sizes and structures. So here, permutation invariant and equivalent means that for graphs, if you permutate the order of the nodes, the output should not be should also either be permutated by the same order, which means it's the permutation equivalent, or the output should not be changed, which means it's permutation invariant. And you can develop the previous framework to other specially designed graph neural network layers so that you can encode many useful relational inductive bases. Here, the message passing framework encodes the message inductive bases such as the localities or translation invariants. However, for many problems, graph neural networks still lack the generalizabilities with respect to the graph scale, such as for the shortest path and many other real applications, such as the navigations or reasonings. You cannot generalize the knowledge from easily generalize the knowledge from the smaller graphs to larger graphs with respect to the graph sizes or diameters. And later on, we will improve these generalizabilities from two perspectives. Firstly, we want to generalize with respect to the graph diameters or the path lengths. Traditionally, graph neural networks are just like as many other graph neural network models, they stack several layers and then output. So given the locality nature of the message passing layers, the receptive sizes of the model are limited by the layer numbers. So for example, if the model wants to send the messages from the bottom left node to the upper right node, although the model can perform well in the training data set, for example, as shown in the red dash ball, it theoretically cannot generalize to much larger graphs. To this end, we introduce a differentiable iterative architecture, which we call the iterative graph neural networks. So the model evaluates the termination probabilities at each time step to evaluate that whether or not stop the iteration now. Therefore, it supports dynamic and unlimited iteration numbers, which means unlimited and unlimited receptive sizes. So it can also perform efficiently during training, but it can generalize to much larger graphs during inference. So how this is implemented? To differentiate an iterative algorithm, the main difficulty is to differentiate this if-stop conditional module. So it has two discrete actions. One is to stop iteration and output. The other is just to continue iterations. To make it differentiable, we firstly relax the discrete action space to continuous ones using the continuous signals. We call it termination probabilities. So if this probability is larger than epsilon, it will continue iterations. Otherwise, it will just output. More importantly, we multiply these controlling signals into the hidden repetitions to achieve the differentiabilities. So gradients passed to H, H here is the final output, and will be passed to C. CK is the confidence to terminate the iteration process at this time step. And will then pass to gradient will be passed to G. G is the controlling module, which is a neural network model that we want to train. Similar, so you have this, all this, you can have a differentiable iterative algorithm. Similar iterations has been applied to recent graph neural network modules such as the short pooling or top K pooling. All of them are multiplying the controlling signals into the hidden repetitions to achieve the differentiabilities, and they perform well in practice. Next, although we now have the unlimited iteration numbers, which means that we have unlimited receptive sizes. The hidden repetition scales or distributions still vary after each iteration, so after each GN layer. And MLPs are known for that they are bad at generalizing to out-of-distribution input. Then notice that many graph-related problems are actually homogeneous functions. So here, homogeneous means that, for example, for the shortest path or traveler salesman problems, if you multiply the edge width by lambda, the outputted path length or total length should also be multiplied by lambda. So if you have this homogeneous pair, you can have some principle or alignment for the out-of-distribution generalization. Therefore, we introduced this homogeneous MLP, which is just MLP without biases and with homogeneous activation functions. We prove that this is a universal approximator of homogeneous functions. So if you just delete all the, so it can only approximate homogeneous functions, and it's universal. So it can approximate any functions to any degree. Now we have some post them. We can show the final experimental results. We evaluate our models on many tasks. Here shows an example of the classical graph theory problems. All the performance are generalized performance, so we train our models on graph with no more than 30 nodes. We'll test them on the graph with 100 nodes. And here we have the shortest path, component counting, and the TSP. Path here is a specially designed message passing layers, and homopath is applying the homogeneous pair to the path model, and iter-homopath is replacing the multi-layer frame architecture with our iterative architecture. And the metric for shortest path and the TSP are relative loss, and for component counting is accuracies. You can see that each proposal, like the homogeneous pair or the iterative architecture, improve the performance a lot. We then perform a deeper analysis of the stopping criteria's behaviors. Here the task is unweighted shortest path problems. And ETHP is our model, which is previously iter-homopath. And you can see that the model actually achieved perfect generalizabilities for these problems. You can train graphs with no more than 30 nodes, and you can generalize to graph of diameters as large as 1,000. We then show that the stopping criteria's behaviors cannot only improve the final performance, it is also interpretable. So here the black dashed line is the half, which means the half of the distance is the iteration numbers. So you need at least this is the theoretically lower bound of the iteration numbers to collect information of the whole path to make an accurate prediction about the shortest path lengths. you need at least half of the path-length iteration numbers to collect all the information due to the locality nature of the message passing layers. So this is a theoretically lower bound, and our model, which is the red line, actually align perfectly with this theoretical lower bound. So the stopping criteria's behaviors are very interpretable. Later on, we will show more experimental results on the more realistic tasks. Here shows an example about physical simulation, and it's a simple environment, just predicting the Newton spot positions and velocities given the previous frame's positions and velocities. And here the performance is also generalized performance, and you can see that all the proposals improve the performance a lot. This is an example about the navigation. Here we share this almost the same task with the previous Pacman, but without ghost. And you can see that this Pacman wants to navigate in the mazes to eat many dots, and we actually generalize the performance to different environments with different number of walls and different number of dots without any fine-tuning or anything, just the zero shot. We then show the benefits of the differentiability. So in many cases, you don't know the graphs and you don't have the knowledge to construct the graphs. So here shows an example of the image-based navigation. The black pixels are dangerous, so agents cannot step on them during navigations. But the model don't know them, don't know it, and it needs to learn it from the data. Given the differentiabilities of our reasoning module, you can easily build any neural networks as the perception modules to construct the graphs. So our model can still generalize from small maps to larger maps. Finally, we show that our model will not hurt your standard generalizabilities. So here the task is the graph classification task. Benchmarks here has some many like biomedical benchmarks or the social network benchmarks. And the JN here is the previously state-of-the-art for graph classification, and the ITER-JN is wrapping each JN layer with our iterative architecture. And the final performance is competitive. So iterative architecture is a safe choice for you to improve your generalizability with respect to graph scales. Now is the conclusion and the summary. So we found that graph neural networks still lack generalizabilities with respect to the graph scales for many problems in respect of the graph sizes, graph diameters, or the edge weights. So we improve the generalizabilities from two perspectives. First is about the graph diameters and the path lengths. So we introduce a differentiable iterative architecture so that we can achieve unbounded receptive sizes by unbounded iteration numbers. Later on, we notice and introduce notice that the hidden repetitions and input repetition skills still vary. So we introduced the homogeneous pair about graph-related problems, and then introduced this homo MLP as a universal approximators of all the homogeneous functions. Finally, we show that our model can zero-shot generalize to much larger graphs on many tasks. Thank you.